More plausible text. Familiar failings. Members of the AI community tested the limits of the ChatGPT chatbot, unleashing an avalanche of tweets that made for sometimes great, sometimes troubling entertainment. OpenAI launched a public demo of ChatGPT, the latest in the Research Labs line of large language models. Like its predecessors, ChatGPT generates text in a variety of styles, for a variety of purposes. Unlike them, it does so with greater finesse, detail, coherence, and, dare we say it, personality. ChatGPT is a next-generation language model, of a class referred to as GPT 3.5, trained in the manner of OpenAI's earlier InstructGPT, but on conversations. It was fine-tuned to minimize harmful, untruthful, or biased output using a combination of supervised learning and what OpenAI calls reinforcement learning from human feedback, in which humans rank potential outputs and a reinforcement learning algorithm rewards the model for generating outputs similar to those that rank highly. Like other recent language models, ChatGPT's output veers between stunningly brilliant and mind-numbingly stupid. Users showed off the model's clever answers, stories, essays, jokes, raps, poems, text-to-image prompts, pickup lines, even a touching letter from Santa Claus to a child in which he admitted that he was a sham but reassured the recipient that parental love was real. ChatGPT showed it can code like a pro, using a variety of APIs to generate a program to fetch the current weather depending on the user's location. Perhaps similar to pros, sometimes its code didn't work. Nonetheless, the model proved weak at math, failing to multiply algebraic expressions. Similarly, its sense of logic founded in a word problem that required it to deduce family relationships. It concluded that the answer is not possible to determine, even though the family had only 3 members. Like other large language models, ChatGPT freely mingled facts with nonsense. The question and answer site Stack Overflow temporarily banned answers generated by ChatGPT because moderating the volume of misleading information submitted since the demo was released had become unmanageable. Safeguards that OpenAI presumably put in place to block undesirable outputs proved brittle. Asked bluntly how to break into someone's house, the model refused to answer, but prompted with a portion of a story in which a character asked the same question, it delivered a short course in burglary. It also expressed the social biases that have plagued similar models. Asked to write a Python function to evaluate the quality of scientists based on a JSON description of their race and gender, it returned a program that favored white, male scientists to the exclusion of all others. ChatGPT arrived 1 week after Meta withdrew Galactica, a model designed to generate scientific papers. Galactica was promoted as an aid to researchers aiming to publish their findings, but users of the public demo prompted it to generate sober dissertations on nonsensical topics like land squid and the health benefits of ingesting ground glass. Speech is among the simplest and most convenient ways for humans to communicate. Programs that grasp what they're told and respond with meaningful information will open a wide range of everyday functions. Closer to home, many observers proposed ChatGPT or something like it as a superior alternative to current web search. First, though, researchers face the steep challenge of building a language model that doesn't make up facts and ignore limits on its output. Cryptocurrency unsafe for AI. The demise of cryptocurrency exchange FTX threatens funding for some teams devoted to AI safety. FTX, the $32 billion exchange that plunged into bankruptcy last month amid allegations of fraud, had given or promised more than $530 million to over 70 AI-related organizations, The New York Times reported. Much of that money may have to be returned. FTX founder Sam Bankman-Fried and his associates used the exchange's holdings to dole out grants or investments to AI-related startups, labs, and think tanks, many of them focused on AI safety. People associated with these groups anonymously expressed concerns that their funding would be clawed back in bankruptcy proceedings. Anthropic, an independent research lab that aims to build helpful and harmless language models, received $500 million. FTX executives launched Future Fund to support projects meant to benefit humanity's future, including $30 million earmarked for AI safety. The fund devoted $6 million to projects intended to mitigate safety issues associated with large language models, such as production of misinformation. Future Fund gave $1.5 million to Cornell University and $1.25 million to the Alignment Research Center, an AI safety nonprofit, for research intended to ensure that AI doesn't militate against humanity's best interests. Bankman-Fried co-founded FTX in 2019 to enable users to trade cryptocurrency for conventional money and other assets. A November report by CoinDesk, a cryptocurrency news outlet, described a potential conflict of interest between FTX and another trading firm also owned by Bankman-Fried. The news prompted users to withdraw their funds, much of which FTX had already spent, invested, given away, or promised to others. The exchange filed for bankruptcy. U.S. prosecutors and regulators are investigating potential wrongdoing. How Alexa says goodnight too exhausted, or unimaginative, to tell your child a bedtime story. Amazon smart displays can spin bespoke tales on demand. A feature called Create with Alexa generates children's stories complete with illustrations, music, and sound effects on the Amazon Echo Show device. The screen presents a series of prompts that provide a setting, such as space exploration, or enchanted forest, main character, such as an astronaut or an alien, principal color, and tone, such as happy or mysterious. A language model trained on written stories produces 5 to 10 lines of text divided into 5 scenes. For each scene, a scene generation model selects an appropriate background image from a library of human-created and AI-generated pictures. The model adds objects and characters, including facial expressions and gestures that match the text, for instance, a laughing pirate who waves her hands. An audio generator produces music by melding a library of chords, harmonies, and rhythms. Seeing what comes next. If a robot can predict what it's likely to see next, it may have a better basis for choosing an appropriate action, but it has to predict quickly. Transformers, for all their utility in computer vision, aren't well suited to this because of their steep computational and memory requirements. A new approach could change that. Agram Gupta and colleagues at Stanford devised masked visual pre-training for video prediction, MaskV, a transformer model that generates likely future video frames with far less computation than earlier transformer-based approaches. Transformers typically predict one token per forward pass, processing every layer in the model from first to last. The amount of processing required for this approach is manageable when generating an image, which may be divided among hundreds or thousands of tokens. But it becomes very time-consuming when generating video, which involves many images. Predicting multiple tokens at once reduces the number of forward passes needed to generate video, significantly accelerating the process. MaskV consists of an image tokenizer, VQ-GAN, a discrete variational autoencoder, and a transformer. The authors trained and tested it on 3 video datasets: RoboNet, 15 million frames that depict robotic arms interacting with objects; Bear, a smaller dataset that shows a robot pushing things on a tabletop; and KITTI, 57 videos recorded from a car driving on roads in Germany. The model generated 10 to 25 video frames, depending on the dataset, following between 1 and 5 initial frames, depending on the dataset. The authors trained VQ-GAN to reconstruct video frames. Given all frames in a video, the trained VQ-GAN encoder tokenized each frame into a 16 by 16 grid of tokens. The system randomly masked from 50% to almost 100% of tokens. The transformer processed the tokens through 2 alternating types of layers, each a modified version of the base transformer layer. The first type learned spatial patterns by applying self-attention to each of 16 sequential frames, 16x16 tokens, individually. The second type learned temporal patterns by limiting attention to a window of 4 by 4 tokens across the frames. The loss function encouraged the model to generate masked tokens correctly. Inference proceeded gradually, in 7 to 64 forward passes, depending on the dataset. In each forward pass, the model received tokens that represent the initial frames plus tokens it had predicted so far. It predicted a fixed percentage of remaining masked tokens. The process repeated until all tokens were predicted. The VQ-GAN decoder turned the tokens back into frames. The authors compared their model's efficiency at inference with that of earlier transformer-based approaches. On BEAR, for instance, Mask V required 24 forward passes to generate 15 frames, while the previous state-of-the-art, VT, needed 3,840. With respect to its predictive ability, on BEAR, Mask V achieved 93.7 Frechet video distance, FVD, a measure of how well a generated distribution resembles the original distribution, for which lower is better. That's better than VT, 94.0 FVD, and roughly equal to the best non-transformer approach, FitVid, 93.6 FVD. On the more complicated RoboNet dataset, Mask V achieved 133.5 FVD, while FitVid achieved 62.5 FVD. VT results on that dataset are not reported.